Okay, now let's move on to pressure. You've probably seen pressure before. Pressure is just force per unit area. Or simply F over A. We'll use pressure, it's a capital P. I'll put a base on it just to differentiate it from rho. Rho also looks like a P, but it's actually a Greek letter, the variable that we use for density. The SI unit for pressure is the Pascal. And this, of course, is after the mathematician Pascal. Mathematician, scientist, theologian, number of things. So 1 Pascal, that's the abbreviation for Pascal, the PA, is equal to 1 Newton per square meter, which are the basic SI units. We also use the unit of atmospheres, and the atmospheric pressure is the pressure at 1 atmosphere, at sea level is 1 atmosphere rather, and 1 atmosphere in terms of pascals is equal to 1 times 10 to the 5th newtons per square meter, or 1 times 10 to the 5th pascals. So it's equal to 100,000 newtons per square meter. So that's actually quite a bit of pressure. This pressure originates from all the gas that sits above you. So if you imagine that you're walking around on the surface of the earth, you have this column of gas that reaches from your head all the way up to the top of the atmosphere. And that gas is sitting on top of your head. So you're like one of those ladies in Asia that have the big basket on their head, except you're walking around with this big basket of gas, this column of gas that rises above your head, and that pushes down on you. And it pushes down on you with quite a bit of pressure. It's 100,000 newtons per square meter. Now we don't usually experience this, or we don't see it anyway, because this atmospheric pressure is pushing at all points on our body. And so the net force as the result of this pressure is equal to 0. I have a couple of things I want to show you. Well, actually, just one thing first. I have this little experiment that you can do and wow your friends that demonstrates the vast pressure that we have at 1 atmosphere at sea level. And you can watch that here. It's a little news clip. So if the atmospheric pressure at sea level is 100,000 pascals, as it is, then what's the force on your body? Well, let's just say that the area of our body, or at least the front part of our body, is about 1 square meter, and that's not terribly far off. It's not 10 square meters, so it's order of magnitude 1 square meter. And I know that pressure equals force over area. So if I wanted to find the force, it's going to be equal to the pressure times the area, which is 100,000 newtons per square meter, times my area, which is 1 square meter, so that cancels out. So I'm left with 100,000 newtons. And we saw that also with the newspaper when the karate chop with the ruler, that there is this vast force that's pushing down. But as I said, the reason that we don't feel it is because, we're walking around, we have this huge force of 100,000 newtons pushing on us, but we also have 100,000 newtons pushing on us from every other direction, such that the net force acting upon us is equal to 0. And so we don't feel it, and we don't usually experience it, except, like for example with this newspaper, which is a nice demonstration that this pressure exists. Let's also look at pressure at a certain depth. This is very similar to the atmospheric pressure, where, remember, it talked about if you're walking around, it's like you have this column of gas that rises up above your head, and the weight of that gas pushes down on top of you. A similar thing is when you're submerged in a fluid. So consider here that I have this block, and it is a height h. It has an area, a face area of A, so the face of that block has an area A, and it has a column of water that extends all the way up to the top and sits on top of that point and pushes down with a certain pressure. Now I know that pressure equals force over area, and this force is going to be the force weight of this column of water. So that's going to equal m times g over the area of the block. Now, this mass the mass of this I can express in terms of the density. That is the density of the fluid times the volume of that column of water that rises up above the point. And so I can say then that P is equal to rho times V times G over A. Okay, so I have this expression here, volume over area, right? But look, volume is just the area of the face times the height of the column. If I wanted to know the volume of this prism, this rectangular prism, of this column of water that rises above, it's going to be the area of this face times this height. That's just the volume in general, is the area of the face times the height. That's true for cylinders, rectangular prisms, cubes, what have you. So these areas cancel out, and I'm just left with H. So I can rewrite this. I can say then that P is equal to rho times G times H. So anytime I go a certain depth underneath the water, then or underneath any fluid or liquid, I'll have this pressure that's just due to the height or the depth that I go. The atmospheric pressure also has to be considered in this. So consider, we have this point. I have this mass of water that sits on top of that point. But then in addition, I have this pressure that's pushing down as well. So I have this additional pressure, which is the pressure due to the atmosphere. Now I know then that the pressure at this point is equal to rho GH, but I also have to consider that pressure that's pushing down up here, that P0. So not only do I have the pressure that's due to the column of the water that rises up above that point, but I also have the pressure of the atmosphere that's pushing down onto the surface of the water. And so the actual expression then is going to be rho GH plus my P0, the pressure due to the atmospheric pressure. I have a little video here of a water bottle that a diver takes, just I think to about 75 feet, and just shows the pressure, how the pressure actually crushes the water bottle. So you can watch this here. The pressures underneath water are immense. I mean, water is very dense and very heavy, so imagine like the floor collapsing under the weight of the water. Imagine, walking around with that column of water over your head. And that's why divers have to be very careful about the way that they, when they're going to great depths, to protect themselves. So you can watch this video here. And you can also go ahead and do this clicker question, or excuse me, this online question.